Cover parametric equations and polar coordinates. We'll begin with parametric equations. An intuitive way of introducing parametric equations is as particle motion moving through a planar field. So if you want to think about like the Earth moving around the sun, at different points in times, it's on this curve that you could graph on an XY plane going around and being in different positions at different months of the year. Now, this you may recognize as an ellipse, and we do have equations for ellipse, but you want to think of it in terms of a function that you input a point in time and it gives you a specific point on the ellipse. We could not describe the motion of the planet, though, as a function of the x-axis, because that would violate the vertical line test. Similarly, we may want to describe the path of a particle or just a curve going through space with the same idea that every point on this curve can be described by just a single point parameter time t, and that gives us a different point on the curve. We want that to be a function. Input one particular value, get out the xy coordinates. And again, we couldn't describe this as a function of x and y, because if you plug in one value of x, you get multiple y coordinates to plot. Parametric equations solves this problem by just giving a function for each coordinate system. It is an input-output function. You give it one time parameter, it gives you one output. But there are two functions, one for each coordinate. We're going to use the notation that f is generally for the x coordinate and y is generally for the y coordinate. We now think of our x and y's as functions of a function of t. We call that t variable, and the interval's over the parametrization of the curve. A first pretty simple example of a parametrized curve that we could graph is something where x just happens to be the same thing as t. So we set x equal to the time parameter t, and y is going to be based on the sine function of t. If we want to graph it, well, we could do this by plotting points on it, or filling in a table and then plotting the resulting points. Now, I'm only going to plot a few of the necessary points or informative points. I'm going to start with the beginning of the curve, which is when t equals -4. When t equals -4, x also equals -4. And to figure out what sine equals, I plug in a -4 into my time parameter and evaluate this sine expression. Just so you know, sine of -4 pi times a 2 is going to be equal to 0, because sine of any multiple of pi is equal to 0. So with the time parameter equal to -4, I can plot the point -4 comma 0, which happens to be over here. I happen to remember the next interesting point for the sine function is half. So if I make my t equal to -3.5 and I multiply that times pi, take the sine of it, that will mean the sine of -3.5 pi is equal to 1 in radians. And that means I get an output of 1 times 2, which is 2 of my function. So for this particular point, I get a positive 2. Now I see a pattern. I know the values of sine. Specifically, I know what angles give me what values of sine well enough to be able to plot the rest of these points. And I remember that a sine function is periodic with periodicity of 2 pi. I understand I'm not plugging in pi's here, but that multiply pi by pi fixes it for me. So this is my period ends up becoming about 2 in this case. I plot the dots with its periodicity, and then I understand that the function for my x-coordinate is continuous, the function for my y-coordinate is continuous, so I'm going to connect these dots with sort of a continuous unbroken curve. From this, I have my crude sketch of the graph of this periodic function, and it really is just the same thing as saying the graph of y equals 2 sine of pi times x, and that's just because t and x are the same thing. But because it's a parametric equation, x doesn't have to be the same thing as t. It can actually be something different, like t divided by 4. So what kind of graph do I get when I graph this curve when I start from t equals -16 all the way to t equals 16? Starting from -16, the x-coordinate is pretty easy to calculate because I just substitute the -16 for my t, and I get a, -4. So I'm going to start from this point over here. Similarly, for the y-coordinate, I plug in a t equals -16, substitute in the equation, and I evaluate it. When I plug in -16 into my time parameter for the y to get the y-coordinate into my function, it ends up simplifying down to that -4 again. And so sine of -4 pi is 0. 0 times anything is 0. And so that means my corresponding y-coordinate would be 0. So I graph -4 for x and 0 for y, which gives me the point over here. If I just take a two-step time step, so it'd be -14 point for my time parameter t, I substitute that into my equation for the x-coordinate, I get a -3.5. To find the corresponding y-coordinate, I do the same trick, plug in a -14 for t there, calculate things, and when I'm done calculating, I get a +2. Thus, the next point I'm going to plot is at coordinates -3.5 for x and 2 for y. I continue this pattern, right? Find the next few points with different time parameters as I plot over here. And I see that I've seen this pattern before, and I'm going to guess that it's going to be the same kind of pattern from here on out. And I crudely draw the corresponding sine waves. Notice that these two different curves are the same. They have the same start point, they have the same end point, they have the same sine wave shape with the same magnitude and the same period. But their equations look different. Well, these are two different parameterizations for the same curves. And when we talk about parameterized curves, this can happen. You can have multiple parameterizations that describe the same curve.